This work is on an elementary complexity upper bound for the bisimulation finiteness problem of pushdown systems and is a collaboration with Pawel Parys from the University of Warsaw. Let me first give you a surely non-exhaustive background on pushdown systems and where they have been used. First of all, they are a well-known and suitable formalism for reasoning about the call and return behavior of recursive programs. For instance, a tool called JMoped has been developed to simulate the execution of Java methods, and with the help of this tool, one is able to automatically detect common Java errors. Moreover, certain security protocols have been verified by making use of the fact that equivalence of deterministic pushdown systems is decidable. Such a central verification problem like reachability is decidable for pushdown systems and in fact decidable in polynomial time. The model checking problem for monadic second order logic, a very expressive logic, is decidable over pushdown systems, however with a complexity that is non-elementary in the size of the formula. The bisimulation invariant fragment of monadic second order logic corresponds to the properties one can express in the model mu calculus, and verifying pushdown systems against mu calculus properties is decidable in exponential time. So pushdown system is given by 4 tuples. The first component is a finite set of control states whose elements we will denote by P, Q, and so on. The second component consists of a finite set of stack symbols whose elements we denote by X, Y, and Z in capital letters. Then we have a finite set of input symbols that we denote in small letters. Finally, we have a finite set of rewrite rules of the following form. Either we have a pop rule, which means when we are in a certain state, Q, and the topmost symbol is X, then we can remove this topmost symbol X by going into some other state Q prime and upon reading a letter A. Or we have a push rule which allows us to replace the topmost stack symbol X by 2 stack symbols Y and Z respectively. It is worth mentioning that we do not have any epsilon transitions and that we view a pushdown system as a generator of an infinite transition system rather than an automaton accepting a context-free language. Let us now define the transition system that a pushdown system induces. The set of all states of this transition system is the set of all configurations of the pushdown system, namely the set of all pairs consisting of a control state and a sequence x1 up to xn of stack symbols that we prefer to depict as on the right-hand side. So let us talk about the transitions. In a nutshell, the rules are being applied on top of the configurations in a last in, first out fashion. Let us first talk about the transitions that are induced by the pop rules. From every configuration being in control state Q and whose topmost stack symbol is X, there is an outgoing A transition to a configuration in control state Q prime, whose stack content is obtained by popping or removing this topmost symbol X if the corresponding pop rule exists. Analogously, one can apply a push rule and hereby replace the topmost symbol X by YZ. And it's worth mentioning that more general rules are possible that, for instance, allow us to replace the topmost stack symbol by even longer sequence of stack symbols, but we do not lose any generality by restricting ourselves to push and pop rules. Here is an example of a pushdown system induced by the following 4 rules, all of which are push rules. So here X stands for 0 and Y stands for 1. That is, going along a 0 transition pushes an X onto the stack, and going along a 1 transition pushes a Y onto the stack. If we now look at the transition system that is induced by these 4 rules, starting at the configuration Qx, we observe that it's the infinite binary tree. Let us now define bisimulation equivalence between 2 states of 2 transition systems. It can be defined as a game between two players, namely spoiler and duplicator. Duplicator claims that the two-pointed transition systems are bisimilar, whereas spoiler claims they are not. The game proceeds in rounds. In each round, first spoiler moves, then duplicator moves. In the first round, spoiler chooses one of the two sides and takes an outgoing labeled transition. In this example, both from S1 and S2, spoiler can only play an outgoing A transition. Spoiler decides to play from S2 and lead the game to the unique A successor of S2. Duplicator must reply by an outgoing A transition on the other side, namely from S1. Given spoiler's choice to play from S2, duplicator does not have much choice but to perform the only A transition that is available from S1. And after this move, the first round is over. Now the second round begins. The game position has changed and we are at the two fat states. Spoiler now decides to move on the left transition system and perform its B-labeled self loop. Duplicator now must answer by a B-labeled transition on the right hand side. She has two choices here. Duplicator decided to answer by moving along a B-labeled transition leading to the lower left state of the right hand side. Round 2 is now over. In round 3, spoiler changed sides again and decided to move along the B-labeled transition leading to the lower right state of the right hand side. Duplicator must answer on the left hand side and decides to take the B loop. Round 3 is now over. In round 4, spoiler plays on the left hand side, not taking the B loop. As an answer, on the right hand side, duplicator takes the B transition to the middle right state. And the reason is that in the next round, spoiler could take an outgoing C transition, therefore it's necessary to move to the middle right state on the right hand side. Round 4 is now over. We can now see that round 5 will be quite boring. The reason is that there are no choices for any of the players, since we are at positions of a pair of states that have both precisely one outgoing C transition and no other transition. Hence, when round 5 is over, we are again in the pair of states we have been in the very beginning. So who wins a play? As expected, any infinite play is won by duplicator. Duplicator also wins if the current game position is actually a pair of dead ends. Dually, spoiler wins if after some finite time he can lead the game to a position that is a pair of states for which there exists some side from which he can play some transition that is not available on the other side. Now we say that S1 is bisimilar to S2 if duplicator has a winning strategy from the game position S1, S2. It is worth mentioning that bisimulation equivalence is an equivalence relation. One can see that from this particular game position S1, S2, one can observe that duplicator indeed has a winning strategy. Hence S1 is bisimilar to S2. Let us now have a look at a pair of transition systems for which spoiler has a winning strategy. First, observe from the two systems S1, S2, the set of sequences that you can execute are the same, so they are trace equivalent. Both can execute A, AB, and AC. However, we claim that they're not bisimulation equivalent, so we have to show the existence of a winning strategy for spoiler to lead the game to a pair of states where you can execute one transition that is not available on the other side. In the first round, spoiler plays on the left hand side, takes an outgoing A transition from S1. Duplicator has no choice but to match the outgoing A transition on the right hand side. On the left hand side, we can observe that we only have available an outgoing B transition, whereas on the right hand side we have available both an outgoing B transition and an outgoing C transition, and this is being exploited by spoiler in the next round. He just plays an outgoing C transition, and such a C transition is not available on the left hand side. So what is the significance of bisimulation equivalence in the context of verification? If one studies those properties in classical logics that do not distinguish bisimulation equivalent transition systems, there are beautiful characterizations of these in terms of classical temporal logics. For instance, a famous result due to Van Bentham states that the bisimulation invariant fragment of first order logic coincides with those properties one can express in modal logic. Similar such characterizations exist for monadic second order logic or monadic path logic in terms of the properties one can express in the modal mu calculus or CTS star. So the question we study in this work is the bisimulation finiteness problem. And it's the following problem. Input a pushdown system and a configuration that just contains one stack symbol. And the question is whether this configuration is bisimilar to some state of some finite transition system. And if this is the case, one also says that the configuration is bisimulation finite. One important remark here is that the finite system is not part of the input. That is, we ask the existence of a finite system that the input configuration is bisimilar to. Only in 2012, Janschar proved that bisimulation finiteness of pushdown systems is in fact decidable. The upper bound consists of two semi-decision procedures. The first one enumerates all finite systems and checks if any of them is bisimilar to the input configuration, a question that is itself decidable, as we will see in the next slides. And the more difficult part of the proof is to have another semi-decision procedure that only terminates in case there is no finite system that the configuration is bisimilar to. It is well known that the regularity problem for pushdown automata is undecidable. However, undecidability only holds in case the automata are non-deterministic. Result due to Velian in the 70s states that decidability can be regained by considering deterministic pushdown automata. Therefore, this result by Janschar can be seen as a generalization of the regularity problem for deterministic pushdown automata. This leads us to a related question, an important central question, namely the bisimulation equivalence problem. And the problem is, given two configurations of a pushdown systems without loss of generality, they just consist of single stack configurations, and the question is to decide whether these two configurations are bisimilar. Sénizergues showed in the end of the 90s that this problem is in fact decidable. Only recently the precise complexity of bisimulation equivalence of pushdown systems has been determined. The problem is actually Ackermann complete. The upper bound has been shown last year by Janschar and Schmitz at last year's LICS, and this year the matching lower bound has been proven in iCalp. These recent results on the bisimulation equivalence problem of pushdown systems, in particular the upper bound, have immediate consequences on the bisimulation finiteness problem of pushdown systems. So it follows that the bisimulation finiteness problem is also in Ackermann. Janschar's proof from 2012 shows essentially that there's a Turing reduction from the bisimulation finiteness problem to the bisimulation equivalence problem. However, as we now know, the bisimulation equivalence problem of pushdown systems is Ackermann hard. Therefore, this approach only gives us an Ackermann upper bound. One important ingredient in the bisimulation finiteness problem of pushdown systems is the following question. Given a pushdown system and a finite system, decide whether they are bisimulation equivalent. Now this problem is much easier algorithmically. So in 2010, Kuchera and Meyer proved that this problem is in fact p-space complete. How is this theorem helpful for the bisimulation finiteness problem of pushdown systems? Well, given a pushdown system and a bisimulation finite configuration, if we can determine a bound on the size of a potential finite system this configuration is equivalent to, it suffices to enumerate all these boundedly many finite systems and check each of them whether they are bisimulation equivalent to the input configuration. The latter is then simply checked using the above mentioned result by Kuchera and Meyer. For instance, and very concretely now, if we can prove that a bisimulation finite configuration is always bisimilar to a finite system of triple exponential size, say, then this would yield a 3x space upper bound for the bisimulation finiteness problem. This leads us to our main result, namely that bisimulation finiteness of pushdown systems is elementary. This means that there's an algorithm whose running time is upper bounded by a tau of exponentials of fixed height. In fact, we can show that the problem is in 6x space. Let us give a brief overview of the proof. So let us fix a pushdown system P and a configuration Q.1. So we can assume without loss of generality that the configuration just contains one stack symbol. So in the first step we show that in case there is a finite system that this configuration is bisimilar to, then there is such a finite system whose size, number of states, can be upper bounded by a function that is sixfold exponential in the size of the input pushdown system. In the second part of the proof, we enumerate all elementarily many such pairs consisting of a finite system and a state of it. And in the third part of the proof, we test if the configuration is bisimilar to the state of the current finite system in p-space using the result by Kuchera and Meyer from 2010. This leads us to our main technical theorem in the paper. Assume a configuration of a pushdown system is bisimilar to a state of a finite system. Assume from our input configuration Qx1 there is a path to some configuration whose control state is, say, Q prime, and its topmost stack content is pink, so to say. It consists of a sequence of stack symbols, and assume that there is a path that pushes the same sequence of stack symbols again on top of the stack. If you can do that once, you can do it twice, you can do it any number of times, and hereby yielding a sequence of configurations of the same form, always copying this pink part onto the stack. So it induces an infinite sequence of configurations. Then if we look at the number of bisimulation classes when always pumping this topmost part, and we inspect the number of different bisimulation classes in this infinite sequence, then in fact, in case this original configuration is bisimulation finite, then in this infinite sequence of configurations there are at most, well, fivefold exponential many bisimulation classes. So this kind of question can be phrased essentially as a decision problem, and this is not a contribution of the paper. So this kind of question has already been posed by Janschar. Yes, given a configuration Q and then some topmost part that is pink and then some bottom part that is white, and let's assume that this pink part can be pumped at infinitum, yielding those infinitely many configurations. Decide whether among those infinitely many configurations there are only finitely many bisimulation classes. And what Janschar proved in this upper bound procedure of his is that this kind of decision problem that we just formulated can be Turing reduced to a suitable equivalence checking problem. However, already one call to the equivalence problem is expensive. We cannot deduce any kind of better upper bound than an Ackermann upper bound. So we need to do something better here. Apart from avoiding the costly detour oracle call to the equivalence problem of pushdown systems, a problem that is Ackermann hard, one main advantage of our proof is that I'm convinced that this proof can be generalized to an even larger class of infinite state systems. For instance, the problem of bisimulation finiteness is even known to be decidable for pushdown systems with deterministic epsilon popping. Janschar calls them first order grammars. And this proof should easily be generalized to this class of infinite state systems. Moreover, there's a plethora of other classes of infinite state systems that allow or that have some kind of pumping property, and this is yet to be explored. This gives rise to a certain succinctness question on pushdown systems, or descriptive complexity kind of question. So how succinct can pushdown systems model finite systems? That is, given a pushdown system of size n, how large, in case this pushdown system has finitely many bisimulation classes, how many bisimulation classes in terms of n can such a pushdown system encode? So this gives rise to the study of the following function s, from the natural numbers to the natural numbers. Given a number n, what is the maximal size s, such that there exists a configuration of a pushdown system such that this configuration is bisimilar to a state of a finite system with s bisimulation classes, and the presentation size of this pushdown system is n. Presentation size, of course, would mean the number of bits to write down this pushdown system that I have not formally defined, but is pretty straightforward. So if we just interpret our main result differently and just express it in terms of this function s, our main result states that s of n is at most sixfold exponentially upper bounded in n, yes? First of all, of course, if we can improve the asymptotics of the function s, then this yields automatically a better upper bound, better asymptotic upper bound on the complexity of bisimulation finiteness of pushdown systems. Any kind of lower bound on s, first of all, doesn't imply anything. It would just show that our approach is not so good algorithmically, so to say. So one can now ask the question still, are there, for the growth rate of the function s, are there any lower bounds known? And in fact, not much is known, as the following slide should explain. So what is the best known lower bound for the growth rate of this function s asymptotically? So what we need to show is that there is a pushdown system of size n presenting a finite system such that this finite system should have as many bisimulation classes as possible. And the best known lower bound is induced by a pushdown system that are given by the following rules. We have n rules. We only have one control state, and this control state is called Q, and we have n stack symbols, x1 up to xn, and the stack symbol x1 can be doubled by applying the first rule, going to x2. Then we can apply the second rule, doubling this x2, pushing two new symbols on top of the stack, and so on. And finally, having only one pop rule, namely by popping the symbol xn from the stack, and then we can observe the finite system that is induced by these n rules. So what is the finite system that is described by these rules? Well, if we start from the configuration qx1, well, we observe that we induce a transition system that just consists of one path of length 2 to the n minus 1. This is of course a finite system, and exponentially larger in terms of the n rules that we described. So this shows that the growth rate of this function s is exponential. Now I must say that, I don't care if this s is like at least 2 to the n square or something like that. So the next step to advance this lower bound would be to show that s is like lower bounded double exponentially in n. However, I believe that s is principally upper and lower bounded exponentially. So let's conclude. In this work we have shown that bisimulation finiteness of pushdown systems is elementary and therefore much easier than bisimulation equivalence. This is a problem that is Ackermann hard. If we analyze our bounds precisely, then this yields an algorithm that is in 6x space. A finer analysis that we have not carried through would yield an upper bound that is 5x space. However, we're not interested in improving this upper bound to a threefold exponential, double exponential upper bounds. The next step would be to determine the precise complexity of the problem. In fact, the best known lower bound to the bisimulation finiteness problem of pushdown systems is deterministic exponential time, and this can be shown by combining two results of Kucher and Meyer and Silva from 2002. Essentially, the idea is to simulate the computation of an alternating piece-based machine by using only the topmost n stack symbols on the pushdown system, or rephrased differently, one reduces from the equivalence problem of pushdown systems by constructing them both to be bisimulation finite. As mentioned above, our proof avoids Orwell calls to bisimulation equivalence, and therefore avoids a Ackermann complexity bottleneck. And as mentioned before, the proof can probably be generalized to a large class of infinite systems, allowing certain pumping properties, as for instance first order grammars or ground tree rewrite systems. So the situation of the regularity problem, or the finiteness problem, so to say, up to bisimulation for deterministic pushdown automata, which do have epsilon transitions, but they must be used in a deterministic way. So the regularity problem is known to be decidable by Valiant in 1975. So that was a point when it was not yet known that the equivalence problem is decidable. And to date, we do only this upper bound has not been improved yet. So we do know that the problem is decidable in double exponential time. This has been shown by Valiant. And the best known lower bound is deterministic polynomial time hardness. And this is just easily inherited from the emptiness problem.